Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on extraction and separation techniques used in refineries and chemical plants, which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to describe the scientific principles associated with adsorption. Describe the extraction process. Describe the stripping process. Identify the basic equipment associated with extraction. Describe the crystallization process. Explain how a scrubber works. Identify the basic equipment associated with the adsorption process. Describe the solvent dewaxing process. Explain the basic components and operation of a side stream stripping column. Before starting the course, let us have a look at key terms. Absorber is a device used to remove selected components from a gas stream by contacting it with a gas or liquid. Adsorber is a device, such as a reactor or a dryer, filled with a porous solid designed to remove gases and liquids from a mixture. Extract is the second solution that is formed when a solvent dissolves a solute. Extraction is a process for separating two materials in a mixture or solution by introducing a third material that will dissolve one of the first two materials but not the other. Feed is the original solution to be separated in liquid-liquid extraction. Raffinate is in liquid-liquid extraction, material that is left after a solvent has removed solute. Scrubber is a device used to remove chemicals and solids from process gases. Solute is the material that is dissolved in liquid-liquid extraction. Solution is a uniform mixture of particles that are not tied together by any chemical bond and can be separated by purely physical change. Solvent is a chemical that will dissolve another chemical. Extraction. One of the most frequently encountered problems in chemical process operations is that of separating two materials from a mixture or a solution. Distillation is one way of making such a separation, and it is perhaps the most frequently used method. Another useful method is extraction. Extraction is a process for separating two materials in a mixture by introducing a third material that will dissolve one of the first two materials but not the other. There are three basic types of extraction: leaching, washing, and liquid-liquid. In leaching, a material is removed from a solid mass by contacting it with a liquid. Metals are removed from their ores by leaching. In washing, material sticking to the surface of a solid is removed by dissolving it in a liquid and flushing it away. You use this process every time you take a shower. In liquid-liquid extraction, all three materials are liquids, and the mixture is separated by allowing them to layer out by weight or density. This video focuses on the liquid-liquid extraction process. Reasons for extraction. Each method of separation has its own advantages and disadvantages, and several situations call for the use of liquid-liquid extraction rather than distillation or some other method. In many cases, it is impractical to separate two chemicals by distillation because the boiling points of materials are too close together. In such a case, it is frequently possible to find a third chemical that will dissolve one of the two chemicals. In this situation, extraction would be a better method of making the separation than distillation. Many chemicals are highly sensitive to heat and will degrade or decompose if raised to a temperature high enough for distillation. In this case, extraction, which can usually be carried out at normal temperatures, would be a practical alternative. Often, one of the materials to be separated is present in very small amounts. It might be possible to recover such a material by distillation, but it is usually much easier and more economical to do so by extraction. Finally, the key requirement of any commercial process is that it be economical. In situations in which several alternative means of separating two chemicals could be used, the one that is the most economical is chosen. Because many relatively inexpensive solvents are available, and because the equipment required for an extraction operation is relatively simple, economic considerations often favor liquid-liquid extraction. Liquid-liquid extraction process. There are basically 3 steps in the liquid-liquid extraction process. 1. Contact the solvent with the feed solution. 2. Separate the raffinate from the extract. 3. Separate the solvent and the solute. Step 3. Recovery of the solvent and solute is left to be done by some other process such as distillation. In liquid-liquid extraction, the feed is the original solution. The feed solution, containing the solute, the material that will be dissolved, is fed to the lower portion of the extraction column. The solvent, the material that dissolves the solute, is added near the top. Because of density differences, the lighter feed solution tends to rise to the top while the heavier solvent sinks to the bottom. As the 2 streams mix, the solvent dissolves the solute. Thus, the solute, which was originally rising with the feed solution, actually reverses its direction of flow and goes out with the solvent through the bottom of the column. This new solution, consisting of solvent and solute, is called the extract. The other chemical in the feed stream, now free of the solute, goes out the top as the raffinate. The raffinate and extract streams are not soluble in each other and will layer out. Properties of a good solvent. The solvent must be able to dissolve the solute, but it should not be a substance that will dissolve the raffinate or contaminate it. It also must be insoluble so that it will layer out. The density of the solvent should vary sufficiently from the density of the raffinate so that they can layer out by the effects of gravity. The solvent must be a substance that can be separated from the solute. It should be inexpensive and readily available, and it should not be hazardous or corrosive. Equipment. Basically, the equipment for commercial operations is designed to ensure contact between the solvent and the feed and to separate the extract from the raffinate. The simplest extraction apparatus is the single-stage batch unit. In such an operation, the feed and solvent are added to a tank or some other suitable container. They are then thoroughly mixed by a mixer in the tank or by circulation in the tank. After the materials have been thoroughly mixed, the mixing is stopped, and the materials are allowed to layer out. The extract and raffinate layers can be removed. Such a process could be converted to continuous operations by continuously adding the feed and solvent and continuously withdrawing the raffinate and extract. For such a process to be successful, some means of mixing or contacting the materials must be provided while still allowing ample space for the raffinate and extract to layer out. Many simple yet ingenious means have been employed for this purpose. Most frequently, a single-stage device as described will not provide a perfect separation, and the raffinate must be contacted again with more solvent to complete the removal of all solutes. This problem leads to the concept of the multi-stage operation. In its simplest form, this could consist merely of a series of single-stage units, coupled close together. In this case, 3 stages are used, but obviously any number could be used. Notice that the solvent and feed both enter the system on the left and the raffinate and extract are removed at the right. The raffinate from each stage is the feed for the next stage, and the solvent for each stage is the extract from the preceding stage. Such a flow pattern is called concurrent, that is, the flows are in the same direction. In effect, such an arrangement is an attempt to use several stages to accomplish the separation that could be accomplished in a single stage with perfect mixing by remixing the materials again and again. A more efficient approach would be to use a countercurrent flow arrangement, introducing the solvent at the opposite end of the chain of stages from the feed. In such a system, the feed to each subsequent stage is contacted with fresher solvent than was in the preceding stage, thus providing a more efficient operation. Such countercurrent flows are almost always used in commercial equipment to provide greater efficiency. Extraction columns. From the previous section, we have seen that an efficient extraction column should provide for continuous countercurrent flows. It must provide some means of mixing the solvent with the feed and yet allow the raffinate and extract to settle out. There are 3 main classifications of extraction columns, which are designed for this purpose: packed columns, tray columns, and mechanical columns. A packed column is the simplest and most commonly used type of extraction column. Basically, it is a hollow shell that has been filled with small objects packed closely together. As a liquid stream flows through this packing, it is divided into many small streams winding their way through the dense packing. The stream flowing upward competes with the stream flowing downward for the same passageways through the packing, resulting in enhanced surface contact. The types of packing commonly used in this process are rings and saddles. Tray columns can also be used for liquid-liquid extraction. The tray designs are similar to those employed in distillation operations. Some common types are sieve, bubble cap, and baffle trays. The principle of operation is similar to that for distillation. In the case of the sieve tray, one stream is made to flow across the trays while the other flows through the sieve holes. Contact is achieved as the tiny droplets of the rising liquid pass through the flow of the falling liquid across the top of the tray. A bubble cap tray should perform similarly. A baffle tray is a device for breaking up the countercurrent flows to provide mixing. Baffle trays could take the form of disc and donut trays or crossflow trays. Obviously, contacting is less efficient with such an arrangement, but it is simpler and less susceptible to plugging than our sieve and bubble cap trays. Finally, the newest and most complicated extraction columns are those with mechanical mixing. These employ some sort of rotating shaft with paddle wheels or other types of mixers affixed to the shaft. Such columns are used primarily when a difficult separation requiring a great deal of mixing must be made. Other mechanical equipment involves the use of ultrasonic vibrations for pneumatic pulsation. The vibrations thus established promote mixing of materials. Extraction column terms and principles. The contact area between the extract heavy phase and the raffinate light phase is called the interface. The term dispersed phase is used to describe the one that bubbles through. The higher the feed rate, the more solvent required. The higher the concentration of solute in the feed, the more solvent required. The product customer specifies partial or total extraction operations. Temperature is not as important in the extraction process as in distillation unless it affects density or solubility or approaches the boiling points. Intimate contact with feed and solvent is required, so good distribution inside the column is needed. Absorption columns. An absorption column is a device used to remove selected components from a gas stream by contacting it with a gas or liquid. Absorption can roughly be compared to fractionation. A typical gas absorber is a plate or packed distillation column that provides intimate contact between raw natural gas and an absorption medium. Absorption columns work differently than typical fractionators because during the process the vapor and liquid do not vaporize to any degree. Product exchange takes place in one direction, vapor phase to liquid phase. The absorption oil gently tugs the pentanes, butanes, and so on out of the vapor. In an absorber, the gas is brought into the bottom of the column while lean oil is pumped into the top of the column. As the lean oil moves down the column, it absorbs elements from the rich gas. As the raw, rich gas moves up the column, it is robbed of specific hydrocarbons and exits as lean gas. Stripping columns. Stripping columns are used with absorption columns to remove liquid hydrocarbons from the absorption oil. To the untrained eye, a stripping column and an absorption column are identical. As rich oil leaves the bottom of the absorber, it is pumped into the midsection of a stripping column. As the hydrocarbons break free from the absorption oil, they move up the column while the lean oil is recycled back to the absorber. Adsorption. Adsorption is the process in which an impurity is removed from a process stream by making it adhere to the surfaces of a solid. It should not be confused with absorption. During the adsorption process, a column is filled with a porous solid designed to remove gases or liquids from a mixture. Typically, the process is run in parallel with a primary and secondary vessel. The adsorption material can be activated alumina or charcoal or a variety of other adsorption materials. The adsorption material has selective properties that will remove specific components of the mixture as it passes over it. A stripping gas is used to remove the stripped components from the adsorption material. During the adsorption process, the mixture to be separated is passed over the fixed bed medium, adsorbent, in the primary device. At the conclusion of the cycle, the process flow is transferred to the secondary device. A stripping gas is admitted into the primary device. The stripping gas is designed to remove or separate the selected chemical from the adsorption material. At the conclusion of this cycle, the stripping gas stops as the process switches back and repeats the process. Adsorption processes exist in a variety of forms. Ion exchange, molecular sieves, silica gel, and activated carbon are all examples of adsorption. These processes are used in such widely varying applications as water softening and as cigarette filters. We will look at two of these processes, ion exchange and molecular sieves, in more detail. Ion exchange. Ion exchange resins are very small, bead-like particles that contain charged ions on their surfaces. You will recall from your chemistry course that ions are atoms that have gained or lost electrons in their outer orbits, thereby obtaining either a positive or a negative charge. A positively charged ion is called a cation because it would be attracted to the negative electrode, the cathode, in an electromagnetic field. Similarly, negatively charged ions are called anions because they are attracted to the positive electrode, or anode. Ion exchange resins are classified as cationic if they remove cations and anionic if they remove anions. In an ion exchange process, the process stream containing the impurities, which are in an ionized form, is passed through a bed of the ion exchange resins. Water treatment is a good example. Hard water contains salts of metals such as calcium, magnesium, or iron. Water treating resins have sodium ions active on their surfaces. The sodium ion replaces the hard ion, the latter remains attached to the surface of the resin bead. Depending upon the use for which it is intended, an ion exchange resin may have any one of a number of different ions active on its surface. Hydrogen ions are commonly used in chemical processes. Obviously, over a period of time, all of the ions available on the surface of the resin will have been exchanged, and no further exchange will be possible. At this point, the bed is said to be saturated, and it must be regenerated before it can be useful again. Regeneration is the restoring of the original ion to the surface of the resin beads. In the case of the water treatment resins, the bed could be soaked in a concentrated solution of sodium chloride, replacing the hard metallic ions with fresh sodium ions. Molecular sieves. Molecular sieves are an example of a different type of adsorption process. The sieves are small, porous solids containing submicroscopic holes. These holes are actually about the size of an individual molecule. Some molecules will fit inside these holes, other molecules, because of their size or shape, will not. One application is the removal of traces of water from an organic chemical stream. The relatively small water molecule will fit inside the pores while the bulkier organic molecule will not. In the isosieve process, kerosene, containing both normal or straight-chain paraffins and isoparaffins with branched chains, is fed to a molecular sieve bed. The normal paraffins fit inside the pores, but the branches on the isoparaffin molecule prevent it from doing so. In this manner, a mixture of normal paraffins and isoparaffins can be separated. This separation cannot be made by more conventional means because the physical properties of the paraffins are too similar. As in the case of the ion exchange resins, a point is reached when all the pores are filled and the bed is saturated. At this point it must be regenerated. Regeneration can be done by another, smaller molecule. Equipment. Equipment for adsorption operation is relatively simple. It consists primarily of a tank or vessel containing a bed of adsorbent, be it ion exchange resins, molecular sieve, or whatever. In most cases, the bed is fixed, that is, the bed is held in place while the process stream containing the impurities is passed through the bed. In a few cases, the beds are fluidized and are passed through the vessel counter-currently to the flow of the process stream. In such instances, the adsorbent particles are separated as they leave the vessel and are passed through a regeneration step. The regenerated particles are then recycled to the system. The fixed bed type is by far the more common adsorber. It contains some type of bed support mechanism to hold the bed in the vessel. This would typically consist of some sort of grid support covered by a wire mesh screen. In some cases, the screen is then covered with graduated sizes of gravel or other solid particles to support the adsorbent. Such support facilities are needed to prevent the very small adsorbent particles from being washed out of the bed. The process stream is usually fed through some sort of sparger or distributor to ensure even distribution across the cross-sectional area of the bed. The process stream is removed through a similar type of device, usually covered with a wire mesh screen to avoid loss of the particles. The process flow through the bed can be from top to bottom or from bottom to top. There are also connections for treating the bed during the regeneration step. In ion exchange processes, there are generally two types of fixed beds. Single bed systems remove only one type of ions, either cations or anions. Two bed systems remove both cations and anions. The type of bed used depends on the process involved and the desired quality of products. In the case of the two-bed system, two different arrangements are possible. The cation and anion resin can be in separate layers or in separate vessels. This would be equivalent to two single beds in series. In the other arrangement, the cation and anion resins are together in a mixed bed. Regeneration of the mixed beds involves more complex steps because the two resins must be separated before regeneration and mixed together again after regeneration. Normally, the resins are separated by size and density differences before the regeneration steps. One item of auxiliary equipment that is usually required is a filter. The feed to the adsorber is normally pre-filtered to remove any solids or trash that would otherwise plug the bed. Operation of an adsorber is quite simple and requires little attention. The process stream is merely passed through the bed. If we pulled samples from different points through the bed and measured the amount of the impurity in each, we would find that for the first portion of the bed, the impurity level would be as high as it is in the feed. Then we would come to a point at which the impurity content dropped off very sharply in a relatively short distance through the bed. Beyond this point, the impurity level would drop off slowly again to essentially zero. If we came back later, we would get the same type of profile, but it would have progressed farther through the bed. Ultimately, we would reach a point when the leading edge of this wave would reach the end of the bed. The make stream begins to show a slight breakthrough of the impurity. From the foregoing discussion, we can expect at this point to have a sudden, major breakthrough of impurity very soon as the main portion of the wave reaches the exit. It is time to regenerate the bed. Regeneration operations take various forms, depending upon the system. If the period of time required to saturate the bed is relatively short as compared with the time required for regeneration, there will usually be an alternate bed to which the feed is switched. At other times, the bed may just be bypassed or the unit shut down while regeneration takes place. Regeneration usually takes place in 4 steps. 1. First, after the bed is bypassed, the process stream is displaced from the bed by draining it or displacing it with another chemical. 2. The bed is sometimes washed or flushed to remove any remaining process chemicals as well as solids, dirt, or trash. 3. The regenerating step itself involves soaking the ion exchange resins or purging the molecular sieves. Finally, after regeneration, the bed must be returned to service. This step involves clearing the bed of the regenerative chemicals and preparing it for normal operations. In some cases, a step called classification of the bed is used. This is an operation in which flows are reversed through the bed, partially fluidizing the bed and loosening it up somewhat. At the same time, broken adsorbent particles and trash are washed from the bed. Abnormal operations. Because the operation of an adsorber is so simple, there is relatively little that can go wrong with it. Two problems that can arise are the disintegration of the adsorbent particles and the subsequent plugging of the bed. Factors that can cause destruction of the adsorbent particles are sudden or wide changes in temperature or the presence of unanticipated chemicals. Mechanical shock can also cause damage. As the particles break up, the bed gets packed more tightly and the pressure drop rises. Plugging from any other source, such as trash or dirt or scum, would have the same effect. For this reason, the pressure drop measured across the bed is an important indication of the status of the bed. Also, contamination, such as organics in a system designed for water treating purposes, blind the ion exchange resins because the organic molecule is relatively large and will shield the ion exchange resins. For this reason, resins are specified for a specific purpose and any foreign material could completely negate the process. Drying. A precise definition of drying that differentiates it from other unit operations, such as evaporation, is difficult to formulate. In general, drying means the removal of relatively small amounts of water or other liquids from solids or gases. Drying a solid is usually the final step in a series of operations, and the product from a dryer is often ready for storage or shipment to the customer. The moisture content of a dried substance varies from product to product. Rarely, a product contains absolutely no moisture and is bone dry. More often, the product has some moisture. Dried table salt, for example, contains about 0.5% moisture, dried coal about 4%. The moisture in air or humidity varies with the temperature. Drying is a relative term in a process and simply means a reduction in moisture content from an initial value to a final one. In many applications, air must be dried before it can be used effectively. If it is not dried, the small amount of water vapor in it can form water droplets and damage, contaminate, or cause a malfunction of the equipment. In other cases, a small amount of a vapor in the air or gas could contaminate the equipment or material with which it comes into contact. A gas dryer uses the principle of adsorption to remove vapor. A literal definition of adsorption is to take up and hold on the surface of a solid. The surface of a solid can trap gas and liquid molecules in such a manner that energy must be added to remove them. Different solids have different abilities to trap molecules, which depend upon the type of surface: smooth, rough, porous, and so on, and the type or shape of the molecule. Examples of this phenomenon are fogging up of the inside of an auto windshield and dew forming on grass. A solid has a limit to how much vapor will adsorb on the surface. It is usually limited to the area where droplets of liquid form. The reason that this is the effective limit is that deposits can be easily dislodged, where a film of liquid normally has to be vaporized to be removed. In a flowing gas stream, dislodged droplets would simply retrain and no effective drying would occur. When this limit is reached, an adsorbent is called saturated. That is, the vapor pressure on the surface of the adsorbent is equal to the vapor pressure in the gas stream. In some cases, when the solid becomes saturated, it is removed, thrown away, and replaced with a fresh, dry solid. In others, the solid can have the vapor removed, usually by heating. This method is called regenerating. The choice of method depends on the economics and time involved. A regenerating gas dryer usually consists of two vessels, beds, containing a granular solid. The solid is specifically chosen for its high adsorbency of the target vapor and ease of regeneration. Piping and valves connect these beds such that the gas being dried enters only one bed. The solids in the other bed are separated from the process so that they can be regenerated. When the first bed becomes saturated, it is switched off the line, the second, regenerated bed is put on the line, and the first bed is regenerated. Two methods are used to determine when a bed needs to be regenerated. One is to use a strict timed cycle, and the other is to measure the moisture content of the outlet gas. When the moisture content reaches a preset value, it sends an alarm or automatically switches the beds. Regeneration can be done in several ways. One method is to heat the bed externally and pass a gas through it. Another method is to pass a gas through the bed while it is at a lower pressure. Basically, the liquid on the surface is vaporized into the gas stream and carried away because of the difference in vapor pressure. The regeneration of the solids in a gas dryer can be considered a small-scale operation of drying the granular product from a chemical plant. In the case of a final product, the quantities are usually so large that special equipment is used to handle it, but the principle is the same. The moisture adhering to the solid is vaporized and carried away by a gas stream because the vapor pressure of the moisture on the solid is lower than that in the gas stream. Scrubber. A scrubber is a device used to remove chemicals and solids from processed gases. Scrubbers are cylindrical and can be filled with packing material or left empty. As dirty gases enter the lower section of a scrubber, they begin to rise. As these dirty vapors rise, they encounter a liquid chemical wash that is being sprayed downward. As the vapors and liquid come into contact, the undesirable products entrained in the stream are removed. As the dirty materials are absorbed into the liquid medium, they fall to the bottom of the scrubber, where they are mechanically removed. Clean gases flow out of the top of the scrubber and on for further processing. Water treatment system. In the past, the chemical processing industry pumped a tremendous amount of water out of the ground for industrial applications. This process was stopped after it was discovered that as the water table dropped, so did the surrounding countryside, a phenomenon called subsidence. The chemical processing industry now uses surface water for most industrial applications. Surface water, water that is drawn in from lakes, rivers, and oceans, must be treated before it can be used. Water treatment systems are designed for that purpose. A series of large pumps take suction off the basin and send water to a series of filters for additional purification. Some filtered water is sent to demineralizers for additional treatment to remove dissolved impurities. Crystallization. Some solids, such as sugar, salt, sand, and diamonds, are crystals. They can be distinguished from other solid forms in that their atoms are arranged in a definite symmetrical pattern that is reflected in their shape. Some may be cubes, others may be shaped like pyramids. In the pure state, all crystals of a particular substance have the same shape and no other. In fact, crystals are the most highly organized type of non-living matter. A large crystal differs from a smaller crystal of the same substance only in that it is larger. The fact that some crystals of the same substances are larger than others illustrate the phenomenon of crystal growth. Living matter, such as a tree, grows by adding layers of building units onto its form. Each growing season, a new limb appears or an existing one gets thicker. A tree, however, can grow a leaf as well as a limb. A crystal can only get bigger. Crystallization can be thought of as the exact opposite of dissolving. When salt is added to water, it dissolves into the water. The salt crystals grow smaller and smaller until they disappear. In crystallization, from seemingly nothing, solids form, and they get bigger and bigger. A crystalline substance, however, will not dissolve indefinitely. For example, salt dissolves completely in water only up to a point. If enough salt is added, eventually the crystals stop dissolving. The water has become saturated with the salt. No matter how much more salt is added, no more crystals will dissolve. Something must be changed in order for more crystals to dissolve. The water must become unsaturated by adding fresh water or heating the saturated water. The exact opposite is done to cause a solution to undissolve or crystallize. The liquid is removed by vaporization, or the solution is cooled. Either method causes the solution to become supersaturated or oversaturated and crystals begin to grow. Crystal growth is a very complex phenomenon, and many outside factors affect it, including the starting temperature, the starting concentration, the amount of mixing or lack of mixing, the rate of cooling or evaporation, contamination, and the presence of smaller crystals. The crystallization process can be either batch or continuous. The size of the crystals is controlled by adding liquid and removing crystals. The equipment used in the crystallization process can range from a simple tank to a combination of pumps, agitators, condensers, and tanks. The primary purpose of this equipment is to control the operating conditions during the crystallization process. In crystallization, the separation is possible because of differences in the size and type of molecules and differences in freezing points, melting points, and solubility. In many cases, crystallizers or centrifuges or both are used. An example of the use of crystallizers is in the production of paraxylene. A feedstock of metaxylene, orthoxylene, and paraxylene is fed into a series of empty vessels. Inside the vessels are rotors that turn constantly. The rotor is attached to a series of mechanical arms. These arms reach to the sides of the crystallizer. At the end of each arm is a fibrous scraper blade. As the temperature is lowered in stages, paraxylene freezes. Paraxylene forms crystals that join together, increasing in size as it freezes. Metaxylene and orthoxylene have lower freezing temperatures and remain in a liquid state. The cake of paraxylene on the walls of the crystallizer is scraped off and dropped to the bottom, where it is pumped to a tank. From the tank, it is sent to a series of centrifuges. The centrifuges separate the cake paraxylene from the liquid and send it to a refinery tank. The crystallization process is the opposite of the distillation process. It uses refrigeration instead of heat to separate the various fractions. Economic considerations determine whether refrigeration or heating systems are used. A centrifuge operates on the basis of centrifugal force. A centrifuge consists of a compartment spun around a central axis. Materials in the compartment separate on the basis of density. When a cooling process is used, the products separate easily because they become denser as they cool. Solvent dewaxing. Dewaxing is the removal of wax from lubricating oils. The wax content is critical in determining the viscosity of the lubricating oil. In cold weather, it is necessary for lubricating oil to retain its ability to flow and lubricate. Lubricating oils are classified into different grades on the basis of wax content. Paraffin wax is made up of paraffin hydrocarbons. These hydrocarbons will crystallize when the oil is cooled. The wax then forms and can be separated by the filter in the crystallizer. Besides the filter method, there is also a press method of filtration. The presses, made with a series of cloth filters, eventually become filled with caked wax. The filters are then cleaned. In modern processes, solvents are added to oil to lower the viscosity of the wax and make it easy to filter. Because of the low viscosity, rotary vacuum filters are used instead of discontinuous filters. The solvents can be adjusted to the feedstock to maximize the efficiency of the filtering. The two solvents used are toluene and methyl ethyl ketone, MEK. Toluene has the ability to dissolve the oil and keep it fluid when it is cold. MEK helps build wax. The solvent dewaxing process has 3 steps. 1. The oil is mixed with the solvent and cooled. 2. The oil is filtered and the wax removed. 3. The solvents are recovered and recycled. This picture shows a typical solvent developing process. In step 1, the solvents are mixed with the waxy oil. The mixture is heated first to ensure thorough mixing and to ensure that the oil stays in solution. Next, the mixture is cooled in separate heat exchangers. The first brings the mixture to about -20 degrees Celsius. This cooling is done by exchange with the cold centrifuge filtrate. Next, the mixture is sent to a chiller. The chiller uses refrigerants such as ammonia or propane. The filter used in step 2 is a barrel made of a coarse metal mesh. The mesh is covered with cloth. The lower portion of the filter is in the oil and wax mixture. The filter turns slowly. The wax builds up on the cloth. To separate the oil, a vacuum draws the oil and solvent through the barrel. The barrel collects the wax on mesh surfaces. The caked wax is sprayed with cold solvent to wash off the remaining oil. The wax is then scraped off as it comes around to the scraper. The wax goes through a trough into a warm conveyor. The solvents are separated and recovered from the wax and oil fractions by distillation in the dewaxed oil evaporator. The solvents are recycled back to the process from the top of the slack wax evaporator. The slack wax and lubricating oils are sent from the bottom of the slack wax evaporator to storage. Extraction is a process of separating two materials by contacting them with a third material, which will dissolve one of the first two materials but not the other. Adsorption is the process in which an impurity is removed from a process stream by making it adhere to the surfaces of a solid. An adsorber is a device filled with a porous solid designed to remove gases and liquids from a mixture. Absorption is a process used to remove selected components from a gas stream by contacting it with a gas or liquid. A scrubber is a device used to remove chemicals and solids from processed gases. In crystallization, separation is possible because of differences in the size and type of molecules. This process relies on differences in freezing points, melting points, and solubility. In many cases, crystallizers and/or centrifuges are used. The crystallization process is the opposite of the distillation process. It uses refrigeration instead of heat to separate the various fractions. De-waxing is the removal of wax from lubricating oils. The wax content is critical in determining the viscosity of the lubricating oil. In cold weather, it is necessary for lubricating oil to retain its ability to flow and lubricate. Lubricating oils are classified into different grades on the basis of wax content. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.